This lesson is about the mathematical verification of the measurement process capability. And hello again to this lesson, which essentially has 3 learning objectives. At the end, you should be able to collect the data relevant for a measurement system analysis and to extract the necessary characteristic values from this data. Furthermore, you should be able to carry out all necessary calculations within the framework of this measuring system analysis, and to assess the suitability of the measuring system. That is, once in relation to the relationship between the tolerance of the characteristic and the overall variance, and once based on the relationship between the variance of the parts and the measuring system. And last but not least, you should know what disadvantages process-related parameters can have. This lesson is divided into 3 chapters. In the first chapter, we collect fictitious data for an example and prepare this data for further calculations. In the second chapter, we then carry out the necessary calculations for the measurement system analysis, and in the third chapter, we briefly talk about the disadvantages of process-related parameters. Let's start with the data collection and preparation for the further measurement system analysis. So, let's start with the task definition. It should be proven that a measuring system is suitable for the measuring task. The product characteristic that is to be measured with this measuring system is the diameter of this piston here. The minimum is 60 mm and the maximum is 60.3 mm. Thus, the tolerance T is 0.3 mm. The proof of capability should be based on the overall variance of the measurement process. The parameter that has to be determined for this is to be abbreviated as %GRR. GRR stands for gauge repeatability and reproducibility. This characteristic value should be below 10% for a capable measuring system. Even if we will go into more detail later, here is a brief explanation of what exactly this parameter means. The 6th of a tolerance of the product characteristic is taken as a reference value. The overall variance of the measuring system should then not be greater than 10% of this reference value. In the table on the left, some characteristic values are already mentioned, which we will determine on the basis of some fictitious measured values. The implementation of the measurement system analysis has been divided into 6 sections. First, the data is collected and processed. Secondly, the repeatability is calculated on the basis of this data, abbreviated EV for equipment variation. Third, the reproducibility is calculated, abbreviated to AV for appraiser variation. Fourth, the characteristic value %GRR is then calculated on the basis of the part tolerance, and the suitability of the measuring system is assessed. Then the characteristic value %GRR is calculated again. However, this time it is assessed on the basis of the total part variance. Finally, the characteristic value NDC is calculated. NDC stands for number of distinct categories and also offers a way of assessing a measurement system. So let's get started with the data collection and processing. For the measurement system analysis, the characteristic should be measured by 3 different people. These are appraiser A, B, and C. There are a total of 10 parts available to be measured. The same characteristic should be measured 3 times by each appraiser. So, measure the same characteristic 3 times on 10 different parts by 3 different people. The results have already been entered in the table on the left. The number of parts n is 10 and the number of measurements per part r is 3. The results of the 90 measurements were entered in the table here. Next are some characteristic values that result from this data. For the calculation of the repeatability EV, the average range, GRR, is required. To do this, proceed as follows. First, the range is calculated for each part, which resulted from the 3 measurements on the same characteristic. For example, this is 0.005 for the first part for appraiser A, 0.012 for appraiser B, and 0.013 for appraiser C. Next, the resulting average range is calculated for each appraiser and entered in the table. The average range for appraiser A was 0.0055. For appraiser B, it was 0.0089, and for appraiser C, it was 0.0103. Now, the mean value must be calculated from these 3 average ranges. We see this on the bottom of the right. GRR has a value of 0.0082 mm and has also been transferred to the table on the left. As said, this value is needed to calculate the repeatability EV. The value x bar diff is required for the calculation of the reproducibility. This is the largest difference that results from the mean diameters per appraiser. To do this, proceed as follows. After the range, the mean diameters must now be calculated. For appraiser A, the mean diameter x bar A1 of 60.1 mm results for the first measurement on the 10 parts. For the second measurement as well, and for the third measurement, the mean diameter is 60.102. The mean x bar A from these 3 values is 60.1007 mm. The same is done for the results of appraiser B and C. A mean diameter x bar B of 60.1004 results for appraiser B and a value of 60.0981 for appraiser C. From these 3 values, you now look for the maximum value and the minimum value and calculate the difference. This is 0.0026 and was entered at the bottom right of x bar diff and also in the left table. As said, this value is needed for the calculation of the reproducibility. We have already extracted 2 of the 3 values we need from the measured values. Now comes the last one. RP is the average range of the parts and is needed to calculate the part variation TV. This is determined as follows. First of all, the average diameter of the 3 measurements must be calculated for each part and appraiser. The mean diameter for each part is then calculated from these values. These 10 values can be found at the bottom of the table. If you now calculate the mean value from these 10 values, you get the value you are looking for RP. This is 0.304 and, as already mentioned, is required to calculate the part variation. With this, we have extracted the 3 required values from the measured values. Now, let's move on to the next chapter. Based on the values just determined, in this chapter we will carry out the further calculations for the analysis of the measuring equipment and assess the result. We keep the values from the previous chapter in the left table. So far, we have not addressed the values K1, K2 and K3 at the bottom of the table. These factors are also required for further calculations and can be found in tables that can be found in the relevant specialist literature or on the internet. The repeatability EV is a measure of the variance of the measured values, which is only caused by the measuring equipment. Hence, EV for equipment variation. This is calculated from the mean range and the factor K1. Entering the values into the formula, we get a value of 0.0048 for EV. And that brings us to the reproducibility AV. The reproducibility AV is a measure of the variance of the measured values caused by the appraisers. Hence AV for appraiser variation. With the known values for X bar diff, the factor K2, the repeatability and the number of parts, as well as the appraiser, a value of 0.00103 is calculated for AV. Now that we have determined the repeatability and the reproducibility of the measuring equipment, the combined total variance can now be calculated from these 2 values. GRR, which stands for gauge repeatability and reproducibility, is this measure of the total variance of EV and AV. If you enter the appropriate values into the formula, you get a value for GRR of 0.00495 mm. Before we carry out the last calculation step, a brief explanation of how the end result is to be understood or what exactly is calculated here. At the very beginning, we talked about the requirements that the measuring system has to meet. One requirement was that the %GRR value should be less than 10%. Then the measuring system is considered to be capable. Based on the tolerance of the product characteristic, a reference value is defined to which the overall variance is put in relation. To get this reference dimension, divide the tolerance by 6. The overall variance of the measuring system should then be less than 10% of this reference value, so that the measuring system is considered capable. If you now calculate the percentage of the total variance GRR, the result is a value of 9.9%. With a value of less than 10%, the measuring system is capable. With the value just calculated, one could actually end the proof of the measuring system capability. But I would like to briefly show you an alternative calculation method. Here, PV is a measure of the variance among the parts, so without the variance of the measuring equipment. This is calculated from the average range RP, which is already known, and the factor K3, which is again taken from a table. With these values, we get a value of 0.09564 for PV. TV is then the total variability, which results from the values for GRR and the part variability. A value of 0.09577 is calculated for TV. GRR is then 5.17% of TV. In this way, too, it was possible to prove that the measuring system is capable. In order to consider a measuring system as suitable, one can also provide further proof. In order to be suitable for the measuring task, the measuring equipment must be able to differentiate between different part qualities. For this, the variance of the part must be much larger than the variance of the measuring system. If the part variation is PV and the variation of the measurement system is GRR, then the quotient of PV and GRR times the square root of 2 should be at least 5. This number stands for the number of different categories, that means part qualities, that can be distinguished. Abbreviated NDC for number of distinct categories. For our example, the result is a value of 27. The requirement is even more than fulfilled. Finally, let's talk briefly about some of the insights gained and discuss the results again separately. First of all, let's look at what influence the tolerance has on the suitability of the measuring system with otherwise unchanged values. We choose 3 different tolerances for this. Once the well-known 0.3 from our example, then half of it, 0.15, and third, 0.05 mm. In our example, we had already proven that the measuring system is capable with a value of 9.9% for %GRR. At half the tolerance, this value doubles to 19.8%. This means that the measuring system would only be conditionally capable. And finally, with a tolerance of only 0.05 mm, the value for %GRR jumps to 59.4. In such a case, the measuring system would no longer be capable. We have just calculated the percentage total variance, %GRR, taking into account the specification of the characteristic. This means the tolerance. Now let's take a look at what can happen if the calculations are carried out purely on the basis of process-related parameters. For this purpose, a part variance of RP 0.3 is assumed. Such a spread is large but realistic. Then we have a spread of 0.1. This would be quite small and really good. And then we have another extreme example with a very good and very small spread of only 0.04 mm. With a variance of 0.3, both requirements are met with 5.17% and 27 for NDC, and the measuring system can be regarded as suitable in every aspect. With a part variance of 0.1 and a value of 15.54%, the measuring system is only conditional capable, but the NDC is still fully fulfilled. Well, and with a part variance of 0.04, neither of the two requirements is met. And this is exactly the problem with process-related parameters. It is possible to have a manufacturing process that produces pistons whose diameters vary within a very small range, just like in our example. In other words, under certain circumstances, the permissible tolerance is not even remotely utilized. A gauge analysis that takes into account the tolerance of the characteristic will consider the measurement system to be capable. A measuring system analysis that does not take into account the tolerance of the characteristic, but only the very small variance of the process result, will possibly consider the same measuring system to be not capable. Well, that was a lot of new information. Therefore, I would like to conclude by repeating the 3 most important key messages. The total variance of the measuring system consists of that of the measuring equipment and the influence of the appraisers. For the assessment, the total variance is set in relation to a fraction of the tolerance or the part variation. The method and the requirements for the measurement system analysis must be agreed with the customer. Several capability values should be determined, preferably with a specialized software. If you found this lesson helpful, please let me know and leave a comment. Thank you for that, take care, and see you next time. Bye.